Okay, it's time and let's continue. I don't know if you guys have been paying attention to the infections per day in United States, but if you're interested, there are some new data coming out, and you can actually try to match it with your SIR model and try to see where this one is going to end. Seems like we're still in the upward trend. It's going to take a while. And yeah, let's see. We were here. Last time we were talking about how to classify all the first order system using TD plane. Okay, and we are halfway done. This is what we were trying to do. And the general one will have 4 numbers, here and here. Then we find we have so many different cases, and all of them just reduce to the same procedure. That is, you want to solve for the determinant of lambda I minus a in order to solve for your eigenvalue. You see? Then we say, well, then the only thing that matters will be this number. We call it a t, and this number we call it a d. And the lambda is basically going to be 2 t plus or minus square root of t squared minus 4d. So do you have real? Do you have complex? Really just depends on, does t squared minus 4d equal 0, is bigger than 0 or less than 0? Okay. Then we find the equal to 0 case. We find d equals t squared over 4. So if we draw the TD plane, t d equals t squared over 4. Then we can basically put the corresponding situations on this graph depending on where your TD point falls. Okay. If the TD point falls on this parabola, you will have the critical damped case. If it's below, you will have 2 distinct real case, and if it's above, you're going to have the complex case. That's basically what we're trying to do. Okay. So first situation, d equals t squared over 4. That corresponds to 1 real root. D is bigger than t squared over 4, which corresponding to t squared minus 4d is less than 0. This is going to give you 2 complex root. Finally, d is below will give you t squared minus 4d is bigger than 0. We have 2 distinct real. So at least that part is done. Okay, all the complex stay on the top. Everything's critical stand on this, and everything real stay below. Of course, after that, even for complex, we still have different cases. Okay, so now we take every single case, we try to expand it. First, we do this. We know we have 2 complex. And we know our lambda equals t plus minus 1/2. Whatever you got here. Okay. Since we already know it's 2 complex, we know it's going to be t over 2 plus or minus some number times I. So this part will be the real part. Now back to the complex. How many different cases do you have? If you have a real part equals 0, you have a center, which is a circle. If it's negative, you have something spiral sink. And if it's bigger than 0, you have something which is spiral source. Okay. That reduced to copy, paste. That reduced to, we can basically put the 3 different cases on here. That is if t equals 0. Remember, this is your t. So if t equals 0, we have the center case. If t is bigger than 0, we have the spiral source. And if t is less than 0, we have the spiral sink. Okay. So far, we have put all the numbers into the right region, above the parabola, to the right or to the left of the y-axis, which give you quadrant 1, quadrant 2. Okay, that's the first case. Now the second case, we have d equals t squared over 4. That means we have one real 0, which equals lambda equals t plus minus, and this becomes 0. Okay, which just give you t over 2. Okay, now what do we have for repeated case? We have only two possible cases. The first one is this, which is a sink. The second one is this, which is a source. Okay, which case do you have really depends on is your lambda positive or lambda negative. In this case, it's already t over 2. Then it reduced to is your t positive or t negative. So t less than 0, you have this. T bigger than 0, you have this. We can copy this. Paste again. We add two more images to this graph. That is, if you are right on the parabola, if you're on the right, you will be a source. If you're on the left, you will be a sink. Where did I get that? Let's see, where is this? Actually, you can do one more step. That is, if you have some lambda which equals 0, which is here, you basically have degenerate, but let's not consider that. Okay. Finally, the last case. Below, d is less than t squared over 4. You clearly have two real solutions. Okay. More precisely, t squared minus 40 4d. All right. How many different cases do you have? You have 3 different cases. Number 1, all of them has two straight line solution. You have source, which means both eigenvalue are bigger than 0. You have sink, which means both are less than 0. And you have one positive, one negative case, which gives you a saddle. All right. Now you just need to decide which case it is. Well, what do you have? Let's take a look. You have t plus this number and t minus this number. Is it positive or negative? Really depends on which number is bigger. Which number is bigger? Definitely t. All right. So if t is positive, what's going to happen? This will be a positive number plus a positive number. Both will be positive. If t is positive, this is negative. You have a positive minus a negative, but the positive number is bigger. So together, it's still positive. Make sense so far? Okay. So when t is bigger than 0, there is a guarantee both will be like this. Similarly, if t is less than 0, what do you have? You have a negative number minus a number. This one is definitely going to be negative. You have a negative number plus a positive number, and then it really depends on which one is bigger. Again, the negative one is going to be bigger in terms of absolute value. So this is also negative. So t less than 0 will give you this. So when are you going to have one positive and one negative? That happens when t equals 0. And the positive one and the negative one will be exactly the same. And the negative square root of t squared minus 40. Sounds good? So the last case, if we copy this, we have done everything above. We have done everything on the parabola. Now we want to do everything below the parabola. And again, we have 3 different situations, depending on which location you are in. If t is less than 0, sink. Bigger than 0, source. Right on this, you have one source, one sink. So together, it's a saddle. That is the final thing. TD plane for any first order linear system with constant coefficient. Nothing new. We just summarized what we have in the new TD version. Again, keep in mind T equals A plus D, and D equals AD minus BC. Let's use it. Since we did so much work, this should save our future trouble, right? So let's do it. This is the system. What's the behavior of the equilibrium 0, 0? Your T is A plus D is 0. Your D is AD minus BC, which is 0 times 0 minus 1 times -1, which is positive 1. Okay. D is 1. T squared over 4 is 0. So D is bigger than T squared over 4. Okay. So what do you have? You have D is bigger than T squared over 4. It's above the parabola. Number 2, your T equals 0. Therefore, it's going to be this case. You will have a center. If you want, you can do the full process, but basically you're just recreating the TD plane for just one picture. Okay. This is the system. We have never seen it before. Okay. But now we don't have to go over anything. T is -1 plus 1 equals 0. D is -1 times 1. Well, maybe we got the same case again. Let's change this one to be 2 to make it a little bit harder. -1 plus 2, which is 1. D is -1 times 2 minus -3 times 2, which is +4. Okay. T squared over 4 is going to be 1 over 4. So definitely D is bigger than T squared. So above, and the T is positive. Above the parabola, T is positive. This one is going to be a spiral source. According to what we had here. Okay. Does everything make sense here? So next time you have a system, T is pretty easy to compute. D is pretty easy to compute. Once you have these pair of numbers, just put them into the right quadrant. You will know which thing you have. This basically saves all your trouble. Okay. Not by any trick, just by automation. That's great. Second, let's talk a little bit more about this. Because you pick a T, you pick a D, you can also pick a E, pick a F, you just name them to be the numbers you want. The worst case, you pick A, B, C, D. That means you pick all the numbers, right? You can always do things like this. But why T and D? This will be especially useful in 3 dimension and beyond. Because for now, it's pretty easy for you to write down the quadratic. T come from here. And the D come from here. But what if you have a 3 by 3 system? What if you have an 8 by 8 system? The same polynomial will not work anymore. Okay. Will this idea still work? The answer is yes, it will still work. That may give you a hint. These two numbers are pretty special. Okay. Let's see what they are. A plus D is easy. But really, if you look at the structure, A plus D is what happens here. That is the sum of all the diagonal of the matrix. This one actually have a name. It's called the trace of A, given by TR A. If you have a 4 by 4 system, 5 by 5 system, just add all the diagonal elements together. That will be your trace. What is your D? Your D is AD minus BC. You have done this so many times before. Now you should be familiar. That is going to be the determinant. And then suddenly you know in 3 by 3, this won't be so easy. But it's still computable. So instead of saying about trace T and D, let's rewrap what we have. What you're saying is basically the behavior of the equilibrium is determined by 2 very important values, the trace and the determinant. Actually, don't do this. Of the matrix. Okay. Then the whole thing will work in 3 dimension, 4 dimension, 5 dimension with the same definition. the determinant won't look so nice. Sounds good? Then the next thing I want to argue is these two are very good signature of the matrix. Why? Here is why. Depending on how much you know about linear algebra, I think so far you get the rough idea. For the same linear transformation, it can be described by a matrix. Okay. But suddenly you have a trouble. That is, your matrix is not unique. Your matrix comes from the choice of bases. For the same linear transformation, if you use a set of base, your matrix looks like this. But if you use a different set of bases, your matrix will look different for the same linear transformation. Did you guys know this before from linear algebra? Should we talk more about it? Oh, okay. So let's think about this. Classic physics example. If you have a thing like this. No. Let's put a wall, and let's do a spring mass system here. Okay. Let's say I want to use a differential equation system to describe the spring mass system. Good so far? How are you going to describe this? Well, it really depends on how you set your coordinate system. If you set your coordinate system to be like this, I have one way of saying it. If you set up your coordinate system like this, which a lot of you do when you do physics, right? Why don't you just set the thing to be on the ring plane? Then every coordinate on this thing will be easy. Can you see that for the same system, if you choose different coordinate system, your matrix end up being different? Make sense so far? Okay. So coordinate system 1, coordinate system 2. For the same linear transformation, this one is going to give you a matrix. This one is going to give you another matrix, which looks different, but they describe the same thing. You can change between these two freely according to something called coordinate transformation. So they can actually shift from one type to the other. They are actually equivalent, even though they may look different. A typical example, something like that. You guys should have done this in linear algebra, right? Change of basis. Okay, so you times a matrix. The same linear transformation in basis 1, the matrix look like this. The same linear transformation in basis 2, the matrix looks different. Then the whole thing about the diagonalization is basically for the linear transformation, if you pick the right basis, your matrix will look super easy, which is diagonal. That's basically what you're trying to do with diagonalization. Okay? Now question, if two systems with different matrix, different numbers describe the same system, no matter which system you pick, a sink should still be a sink, right? And the source should still be a source, and vice versa. It cannot say, well, if you use coordinate system 1 for the same for the motion, you get a sink and you get a sink or you get a saddle. But if you do it in coordinate system 2, which is basically artificially put by yourself, and suddenly you got a different behavior, that doesn't make sense, right? So two different metrics describing the same system should receive same results. Let me write it down. This should not be dependent on the coordinate system. The choice of the coordinate system or just the choice of the basis. Therefore, if you want to use some value to describe the thing, you better use some value that does not change under the change of basis. You do it in coordinate system 1, you got these two numbers, t and d. You do it in a coordinate system 2, which you got a different matrix, but you should still have the same t and d because your behavior depends on t and d. So t and d cannot change no matter which coordinate system you choose. Does that make sense here? All right, so that's the requirement. T and D, or whatever value you choose to describe the behavior, should not depend, now let's use the terminology, should be invariant under coordinate transformation. Okay, that's the key requirement, should be. Now, fact, they are not. So T is invariant. And number 2, D is invariant. So they are good indicators because no matter which coordinate system you pick, they stay the same. Therefore, the behavior stays the same because the behavior depends on these two. Okay, so this is actually the best choice. The trace and the determinant. To let you see this, just take any coordinate transformation. You have A, but then if you do coordinate transformation, you have A equals PB, P inverse, where P is the coordinate transformation. So basically what you want to prove is if P is a coordinate transformation, then the trace A should equals trace B. That means even if you change the thing, the trace stay the same. That must mean determinant of A should equals determinant for B. Okay. Then basically what you need to show this equals this. Ah, yeah, I should do the different one. This should be a B. B, determinant PB, P inverse. Okay, now for the proof, if you think about it, this is something you know in linear algebra. Determinant can be decomposed into this, into this. And then you can switch the order. Because they're numbers now. And these two numbers together give you 1. Therefore, the whole thing equals determinant of B. Let's say equals 1 here. Okay. Is every step clear here for the determinant, we basically use a fact that determinant of A times B equals determinant of B times A. We use this fact. Did you guys know about this fact before? Okay, so do you know what determinants stands for? Okay, it stands for when you do the change of basis, right? It stands for how the area is going to change, right? So if you have something, you double the area, then you triple the area. It's the same as triple the area first and then double the area. Okay, so that's determinant. For trace, you have something similar. You have a fact, which is trace A times B equals trace B times A. This is the fact. You can easily prove using IJ notation. But once you have that, then you can switch the order of them. Because P times P inverse is I. Okay. So the key fact, you need this, you need this. All right. So given a matrix describing a system, we pick the signature of the matrix, which is the trace and the determinant. The good news is when you change the basis, the matrix may change, but the trace won't change and the determinant won't change. Therefore, the behavior of the system won't change. So TD plane is actually an awesome way to describe the behavior. And it works for higher dimension than 2. All right. Any questions before we move on? All right. Trace is very important. If I recall, in linear algebra, we didn't introduce this concept probably here. So you will see it a lot later. Just some side topic, the trace of a matrix, okay, especially when A is a probability. Density matrix. Okay, the trace is basically going to give you the total probability. Usually it should equals 1. Okay, but you do have some cases when this one is less than 1. So this one does have physical meaning. Determinant of A, of course, stands for the volume change produced by the linear transformation. And if you recall, both of them actually are related to your eigenvalue. So of course, they give you all the information about your eigenvalue. Okay. If no question, 3.8. Linear system in 3D. We did the face portrait for all the possible cases, spiral, center, two straight lines, things like that. Okay. In 3D, 4D, or even higher dimension, how do we do it? Well, can you still do eigenvalue? Can you still do eigenvector? The answer is yes, I can still do it. It's by linear algebra, for example. Let's take an easy example. Do you still have eigenvalue? Yes. Can you still find eigenvector? Yes. Okay. Can you still draw the face portrait? Well, for this case, can you see that we have three straight line solution? Each one on this direction. So what we have is, we have x, we have a y, we have a z. In the x direction, we have -1, so we do have a sink in this direction. For 0, 1, 0, we do have a sink in this direction. Finally, to the third direction, we do have a sink. Okay. If you want to use what you had in 2 dimension, well, this is your x and y. Of your face portrait. Now, basically what you have is, as this thing move in this thing in the xy plane, you also have a z direction. Still okay? So as you move in, you also move down if you're above, or you move up if you're below, according to the z direction. Can you see that the same idea still applies? All right. Let me open this, that, and the desktop. Okay, so let's take this one. We have a matrix, -1, -2, -3. I use MATLAB to find the eigenvalue to be -3, -2, -1 with the corresponding eigenvectors. So we have 3 real, distinct real. The whole thing look like this. How do I? Okay. You can still draw the slope field. This one tells you at each direction where this thing should go by the face portrait. And if you start from some of them, you can see, well, number 1, in the z direction, you should go down. In the x direction, you should go in. And in the y direction, you should also go to 0, 0. So together, the whole thing traces this thing and go to 0, 0. It's a sink. Sounds good? If you really draw out all the possible streamline, which is extremely hard to see, but I will give it a try. Not this one. Okay. Continue. What's going on? Let's see. Well, perhaps it just takes long. Well, That's the best I can do. Okay, all the straight line, if you see it, it actually all goes back into the 0, 0. And if you try to rotate it, okay, to see the XY plane, you got exactly what we had for 2 dimension. Sounds good. Now it's just as you trace into it, it also goes out of the screen or goes in the screen, depending on which stage you are. That's how you got something look like this. All right. Does everything make sense so far? Okay. Now think about other cases. If you have 3 roots, what can happen? Well, it's very possible that you have 2 complex and 1 real. Okay. For the 2 complex, what's going to happen? You're going to have a spiral. For the 1 real, what's going to happen? You either go away or you either go down. Okay. So together, all together, what should that thing look like? That thing should spiral, meanwhile go up, or spiral, meanwhile go down as your phase portrait. So let's see an example like that. Which one was this? Let's see. Okay. The matrix. Let's redo it. The matrix is 0, 1, 0, like that. Okay, whatever. You did the complex eigenvalue. So you have eigenvalue, which is plus I, eigenvalue minus I, and you have the third eigenvalue, which is real. Okay, which is -3. Plus I and minus I should give you something which is a center. Okay. -3 should give you something which is a sink. Okay, so together, what's going to happen is you are going to be going around as a center. Meanwhile, you go to 0, 0 because you have a sink in that way. So that's what we observe here. Okay, similarly, the last example. Okay, this time you have something goes down with a -3, but your 2 complex value give you something like this. While they're complex, plus they have a negative real part, so they are a spiral sink. So they spiral down. Meanwhile, they spiral sink to 0, 0. That's what you observe here. Okay. That's basically our analysis for 3 dimension. Okay. So let's just do a quick example. Something like this. We just did. 2, -3. What you have is something like this. Okay. Everything's like a streamline, just goes right towards 0, 0. So sink. Number 2. Lambda 1, lambda 2 give you I. Lambda 2 give you negative I. And lambda 3 give you -3. If you just look at these two, what you should have is a center. Okay. But there is a third thing which tells you not only you are going to go in XY direction, or actually V1, V2 direction. In the third direction, you should all go to 0, 0 because it's -3. Sounds good? So together, what you will see is something start as a thing, and that thing start to have a circle, but it circles down, and eventually stays at xy plane and just keep circling. Okay, because everything should eventually go to 0 in terms of z direction. Okay. Does everything here make sense? So we don't need more examples, right? Cool. Then I will just write down. Try by yourself. You have many cases. You can have 3 real, 1 is positive, 2 is negative. 2 is positive, 1 is negative. You can have 1 real and 2 complex. Okay, you can have 1 repeated real, repeated for 3 times. You can have 1 real, repeated for twice, and then another real. So you have all kinds of cases. So far, I think you should know how to do it then. For n by n, it's the same thing. For example, if you have 5 by 5, you just have a lot of cases to think about. 5 real, maybe some of them repeat, positive, negative, and maybe they can have 2 complex plus 3 real, or they can have 4 complex plus 1 real. Okay? But if you do the projection, everything is a similar idea. All right. Finally, the equilibrium. For higher dimension, you have a sink, you have a source. The idea is quite straightforward. You have a sink if all real are negative. Okay. You have a source if you have all real. And they are positive. Okay. That's one case. You also need to count in the spiral sink in certain directions. So you have all real eigenvalues are negative, and all real part of the complex eigenvalues are also negative. Then you have a sink. All real part of the complex eigenvalues are positive. So a combination of straight line source and a spiral source together, okay, it's going to give you a source. Number 3, settle for everything else. Some direction you are a source, some direction you are a sink or spiral sink, whatever, doesn't really matter. As long as they're not all sink or all source, settle. Okay. Any question regarding this? Go back, work on chapter 3 is over. Work on chapter 3. Basically, just to tell yourself how many different cases you have. Okay, when you look at the eigenvalues and what does each case mean. Make sure you can draw the phase portrait for each one. Make sure you know how to determine it's a sink, source, or settle. Okay, and make sure you know how to interpret the results if you do them separately in the, for example, in the harmonic oscillator case. That's all we need for chapter 3. Okay, if you have questions, stay. Otherwise, the class is over.